All right, we're going to talk about introduction to radicals. We know a little bit about radicals from a different unit before, and what we're going to basically be doing in this particular section is going to be simplifying radicals, but with higher roots as well. So we'll get into some definitions, some examples, and kind of go through that way as well. So what we've done before was we had a root, and say the root was 25, right? And, well, that's a square root, so square root of 25 would be 5. Then we also had problems where we had the square root of, say, 48. And there were two different ways to actually do this. There was two ways that we kind of talked about in class. The first way was to take 48 and to prime factor it. Remember, it was 2 times 24, it was 2 times 12, and then 2 times 6, and then 2 times 3. And then because it was a square root, we had to work with pairs of numbers. So remember, in each pair, I would take one out, okay? And remember, the other one, we said like it got lost or it got kidnapped or whatever happened, so that would get crossed out. And then the two numbers that were circled, okay, would come outside in front of the square root, and they'd be multiplied together, right? 2 times 2 is 4. And then the number that didn't get touched, right, it didn't have any friends, which was this 3 right here, that would stay inside. Okay, and that's how we would, that's one way we could do that. Another way we said was we could take the number 48 and we can see what perfect squares go into it. So remember, it's 1 times 48, it's 4 times 12, 9 can't go into it, 16 can, it's 16 times 3, 25 can't, 36 can't, and then 64 is too big. So we know we got to pick the biggest one, so we would use this one here, and we would take the square root of 16, take it out, which is 4, and then the 3 would be left inside. So we get the same answer both ways. But that's when we deal with square roots. Okay, square roots, we know that the root is a 2. Okay, there's technically a 2 in our square root, right? Square means 2. I don't have to write that 2. Okay, this is basically invisible. Okay, but it's understood that it's a 2 when I don't write a number there. We're going to be dealing with higher order roots in this particular section, and higher order roots where that 2 could be a 3 or a 4 or 5 or a 6 or a 15 or whatever. I mean, we're not going to get that high, but it very well could be. So we need to come up with some different strategies to use for those particular roots. So let's start with a very basic one here. We'll take the third root. Well, how do I know? Because this is a 3. Because that 3 is there, we know that it's the third root. That number tells me, well, again, what root I'm dealing with. So we'll take the third root of 8, or the cubed root of 8. Now, we can memorize some certain cubed roots, or fourth roots, or fifth roots, or sixth roots. It's going to kind of get cumbersome when we get to really, really big roots. So if you did the last section this way when we talked about square roots, if you did, say, 48 this way, and then 16 times 3, if you did the last section this way, then I might strongly recommend you change it to this way here. And I'll explain why. So we got 2 and 12 and 2 and 6 and 2 and 3. So I get the same answer both ways, but again, this way, which is the prime factorization way, might be the best alternative when we get to higher roots. And the reason for that is because the third root means we need to have groups of 3. Square root was groups of 2. Seventh roots are groups of 7. Okay, we need to have that many in each group. So if I break down 8, it's actually 2 times 4 and 2 times 2. So the cubed root of 8 is actually 2 times 2 times 2. Now, because it's a 3 outside, that means I need a group of 3 numbers that are the same. Therefore, I am going to only take one of them out, and then the other 2 kind of disappear. That's what happened before. They don't actually matter. So the third root of 8 is actually just 2, because 2 to the third is equal to 8. Okay, we have cubed roots and exponents. They kind of go hand in hand, but we're just going to talk about radicals right now. We'll get to exponents in another section. So let's get into some maybe harder problems. Okay, so let's do the cubed root of, let's say, 48. Cubed root of 48. Okay, well, we know 48 from before. We know it was 2 and 24, 2 and 12, 2 and 6, and 2 and 3. So the cubed root of 48 is actually 2 times 2 times 2 times 2 times 3. We have 4 2's and 1 3. But it's the cubed root now. It's not the square root as we had before. So I need groups of 3, not groups of 2. Well, what happens? One of those 2's pop out, the other 2's disappear. So the one that popped out comes out. The numbers that didn't get touched by circling or crossing or boxing or whatever, which is these 2 and the 3, they stay inside. But what do they stay inside as? They stay inside as a 6. 2 times 3 is 6. So our answer for the cubed root of 48 is actually 2 times the third root of 6. Now, that's all well and good, and we can do cubed roots and fourth roots and fifth roots all day, but what happens if we have a variable in there? So let's take the fourth root of some variables, and let's not do with some numbers yet. Let's do some variables. So let's do y to the 10th, z to the 12th, okay? So this looks kind of crazy. We're like, what's going on here? We need to figure out what this actually means. There's kind of a couple different ways you can do the variables. The long way would say, what does y to the 10th actually mean? It means I just have 10 y's. So there's 5, 6, 7, 8, 9, and 10. And then I can go through and I can box 4 of them. Right, I can box 4 because it's the fourth root. I can circle 1, the other 3 get canceled. I can do the same with another 4, circle 1, the other 3 gets canceled. And then I don't have another 4 y's, so I have to leave those 2 inside. But there's actually an easier way to do this, is if I say how many 4's go into 10, you're going to say, well, 2 of them go into 10. Exactly. So that means I can pull out 2 y's. If then I say, well, how many 4's go into 10? How many's left over? You're going to tell me that you have 2 y's left over. Because 4 times 2, multiply those together, that's 8. And then plus the 2 gives me the 10, which is what I started with the 10 inside. Then you're going to say, okay, how many times does 4 go into 12 here for the z's? Well, that's 3. And that's exactly 3. So our answer for this particular one with the y to the 10, z to the 12 inside is we have 2 y's that popped out, we have 3 z's that popped out, and we have the fourth root of y squared still inside. Now you notice this 4 is kind of like in this little hook. That is how those roots should be written. If you write the 4 kind of out here somewhere, that means it's going to be an exponent, and I am going to get confused, and you will probably get confused as well. So please write the 4 inside this little hook, okay, with the root, with the radical. So that would be our answer for that particular example. Now let's get into some examples for this particular section. So on the board, here we go. Here's question 1 on your packet. And so this is now a square root. Remember, there's a little 2 kind of, invisible, but it's implied that it's a 2, it's square root. So I'm going to take the 320. Remember, I said the easiest way is to probably factor this way with prime factorization. So that's 2 160, that's 2 and 80, 2 and 40, 2 and 20, 2 and 10, 2 and 5. Well, it's a lot of 2's. So this is actually the square root of 2 times 2 times 2 times 2 times 2 times 2 times 5. We have 6 2's and 1 5. Now because I'm dealing with a square root, I'm going to put these in groups of 2. And then within each group of 2, I am going to take one of them out, cross the other one out. Take one out, cross it out, take one out, cross it out. So how many 2's came out? 3 of them. So 2 times 2 times 2 is 8. The 5, which is right here, is going to stay inside because I didn't touch it. Okay, whatever you don't touch stays in. Now, let's look at the variable n squared. We talked about before. How many times does this 2 go into that 2? Well, 1. Anything left over? No. So I don't have any n's left inside. So my answer is 8n square root of 5. So 8n times the square root of 5. You don't have to put the exponent of 1, but you're more than welcome to do so if you want to. Go ahead and try this particular example. Hit pause and then hit play to see if you're right. So here we go. Again, I want to take 343 and I want to break it down. We know that 2 can't go into it. Can 3 go into it? It cannot. Can 4 go into it? No. 5, no. 6, no. 7, I believe 7 can. And 7 times what? Should be 7 times 49. And then 49 is 7 times 7. So, in this particular example, I have, remember it's a square root, right? It's as implied that I have 7 times 7 times 7 times n to the third, okay? So, I take a group of 7s, a pair of 7s. Then I'm going to take 1 out, cross 1 out. So what happens? How many did I take out? I took 1 7 out. This 7 here stays inside because I didn't touch it. Then, how many times does 2 go into 3? 1 time. Do I have any left over? Yes, I have 1 left over. So 7n times the square root of 7n is your answer for this one. All right, let's go number 4 here. I skipped number 3, that's all right. Now you notice I have some different ones here. Again, it's a square root. Okay, but I have a negative 2 out front. We'll deal with that in a little bit. I'm going to start with my number 24. I'm going to say 2 and 12, 2 and 6, 2 and 3. So I can rewrite this as 2 times 2 times 2 times 3, x squared, y to the 4, z squared, with that negative 2 popped out. And remember, it's a square root, so I got the 2 there. You don't have to write it, but just to make sure you know what you're doing. Now I need groups of 2. So there's the group of 2. Take 1 out, cross the other one out. So you notice the 2 and the 3 that I didn't touch are going to stay inside. So you know that there's going to at least be a 6 inside because 2 times 3 is 6. The 2 that I circled in red and popped out is going to get multiplied to the number that's out front. That's always going to happen. All the numbers that pop out get multiplied with the coefficient of your root. Whether it's a negative 2 or a positive 7, you're going to multiply the number with it. That 2 is again still there. You don't have to write it. I'm just letting you know that it's still there. Now I'm going to look at my variables. 2 goes into x how many times? Or that, the exponent of 2. Well, it goes in 1 time. I don't have any left over because it goes in evenly. This 2 goes into y to the 4 how many times? Well, that's a 2. How many times does this 2 go into z squared? Well, just 1. Okay, so you notice I'm a little cramped here, so I'm going to rewrite it. Negative 4x y squared z times the square root of 6. And again, you don't have to put the 2 inside the little hook, but you can if you want to. I don't want to, so I'm not going to. So there's my answer for this one here, number 4. That is how I simplify. Go ahead and try this one here, number 6. Pause video, and then hit play once you get done. All right, I'm still, again, dealing with square roots. So I'm going to take the 147, and I'm going to try to factor. This can be divisible by 3, so it's 3 times 49, and then I have a 7 and a 7. So I have 4, which is still there up front, times the square root of 3 times 7 times 7, x squared, y to the 3, z to the 3. I'm looking for pairs of numbers. Why? Because there's technically a square there, right? It's a power of 2, or the root of 2. So I'm going to take these. One comes out, the other gets thrown in the trash. So the 7 came out, multiplied with the 4, and became a 28. This 3 didn't get touched, so we know it's going to stay inside. Now let's look at my variables. How many x's pop out? Well, hopefully by now we're looking at them and we're saying, oh, hey, only 1 pops out. How many y's pop out? 1 pops out, but 1 stays in, because 2 goes into 3 one time with 1 left over. And then how many z's pop out? Once, and then 1 stays in because, again, 1 pops out and there's 1 left over. So this is my answer. 28xyz times the square root of 3yz. What I like to do is I like to add a little kind of hook on the end of it. This just tells me this is the end of what's in the square root. You don't have to do that. Make sure your square root is fully extended over what's inside. You don't have to make sure your square root's like way over there if there's only, if it stops right in here. Okay, just again, make sure your line above your numbers go to the end of what numbers you actually have written. Let's do these 2 problems here, 11 and 12 together, and then you'll have some to do yourself, and we should be good to go. Okay, so let's start with 11 here. The cubed root now is the third root of 256, so I'm going to take 256, I'm going to break it down. We know it's 2 times 128, 2 times 64, 2 times 32, 2 times 16, 2 times 8, 2 times 4, and 2 times 2. There's a lot of 2's there. So you have the third root of how many 2's? 1, 2, 3, 4, 5, 6, 7, 8 2's. Wow. 3, 4, 5, 6, 7, 8, and then the end there. So I'm not dealing with square roots, so I don't have pairs of 2's. I'm dealing with third roots, so I'm dealing with 3 of the same numbers. So what happens in each of the group? 1 pops, 2 get crossed. 1 pops, 2 get crossed. So the 2 numbers that popped out make a 4. And these 2 2's here that didn't get touched, they stay inside as a 4. 2 times 2 is 4. Now, look at my variables. Can 3 go into this exponent there of 1 on the end? It can't, so that means no n's can pop out, so that means n has to stay inside. So this is my answer for number 11 there. Let's go to number 12. All right. Now, you might be looking like, well, I have a negative in there. That kind of is confusing. So here's kind of some background on this. When I have an even root with a negative inside, okay, this cannot happen. Why not? Well, because when I take an even root, so this is an even root, I can never multiply 4 numbers. So this is even as a 4, right? So say negative 3 times negative 3 times negative 3 times negative 3. If I multiply these together, I get positive 81. I never get a negative number when I multiply 4 of the same numbers together. But when I have an odd root, that is a plausibility, meaning that negative 1 times negative 1 times negative 1 times negative 1 times negative 1, 5 times, or an odd amount, you get a negative number. So negative 3 times negative 3, 5 times, you get a negative number, okay? So an odd root, here, you can get a negative inside. It is okay. It's not, a bad thing. Your calculator would even calculate it as well, okay? With an even root, that's not going to happen. How do we actually calculate this particular example? Well, because it's an odd root with a negative inside, we're going to kind of forget about that negative real quick. We're just going to take about the 96, okay? So it's 2 times 48, 2 times 24, 2 times 12, 2 times 6, 2 times 3. So let's rewrite this. We got the 5th root of a negative. We'll just leave it there, but it really doesn't matter right now. And then we have a 2 times 2 times 2 times 2 times 2. We have 5 of them times the 3. Okay? So what actually happens, and then we have the v squared, I guess, at the end. I just forgot about that. So what actually happens, because we have the fifth root, I need groups of 5. Well, we have 5 2's, so that's pretty good. So I need one of them is going to pop. The other 4 are like long lost friends. You don't even know they're there. Okay, so the 2 pops popped out. The fifth root is still there. This 3 didn't get touched. And how many times does the 5 go into the 2 here? Well, it doesn't go in evenly, so that v squared has to stay in there. But what happened? I forgot about this negative. Well, whenever you have an odd root with a negative inside, the negative just pops out. So your answer is -2 times the fifth root of 3v squared. So there's your little shortcut for negatives, okay? If there's a negative inside with an odd root, the negative just pops. If there's an even root with a negative inside, that's not possible. You'll never get an answer that way. Okay, go ahead and do 15, 16, and hit play once you have them done, and then we'll see where we're at. Okay, with 15 here, let's go through 128. So we got 2 and 64, 2 and 32, 2 and 16, 2 and 8, 2 and 4, 2 and 2. Oof, that's a lot of 2's again. We've got a lot of 2's in these problems. So we have, how many 2's? We have, looks like 7 of them. So 1, 2, 3, 4, 5, 6, 7, x squared. Because I have the fifth root, I need 5 of the same numbers. So 1 pops, the other one, I don't know, get thrown in the trash. Okay, so the one that pops comes out front. How many 5's go into this x squared? It can't go in evenly, so we know that has to stay in. These 2 2's that were left, haha, 2 2's. The 2 2's that were left stay inside and makes a 4. So it's 2 times the fifth root of 4x squared, because the x squareds can't pop out, and the 2 2's left inside have to stay in there as a 4. So let's go to 16. Well, what did I say? Odd, and there's a negative. So what happens to this? It just automatically pops out. So we know we're going to have a negative outside in our answer. Well, let's take 128. If you look at 5, we already had 128. So it's actually 2, 2, 2, 2, 2, 2, 2. It's 7 of them. We have the negative out front. That's going to be there. We have 7 2's, 4, 5, 6, 7, and then 1a. Remember I said make sure your bar above the numbers go to the end of what you're actually doing. So what happens? Because I have a third root, I need to take 3 groups, or groups of 3. 1 pops, crossed out. Pops, crossed out. The numbers that pop make a -4 because the negative's already there. 2 times 2 is 4. Third root of that 2 stays in, and that a stays in because it's the third root and they don't go into my variable. So there you go. That is how you simplify radicals. Now again, some of your roots will be higher powers, 5, 6s, 7s. That doesn't really matter. It's the same principle of all of it. Remember, we have a number outside. Multiply that number outside by the numbers that pop outside. And there you go.